Hello.
Hola. How are you
Good
guys?
morning.
Well, I got a project on the linear algebra, so was just talking with Ben about it.
Nice. That is Mary Middleton's class. Yes.
Mhm.
Very painful. Daniel's here. Sweet. Let's get into it. All right, sharing screen. Bring a few examples in. So we're launching into chapter 14, and I will pull up the note sheet right now that you want to be staring at. And we have, and we're not done with these, but we have played with all of these fine formulas. Now it's time to talk about today, work and energy, and tomorrow, Thursday, power and conservation of energy. Daniel brought this up a while ago as an easier method. And so we're going to take a look at that now. I want to do a couple introductory things though. The mathematician in me and the curious person in me wants to kind of make sure you understand where these formulas come from, because you should look at work equals force times distance and kinetic energy equals 1/2 mv squared as just some new physics equation that, who knows why that's true or where it comes from, but let's just use it and get on with it. But I want to show you something kind of neat. And to do that, let's back up a little bit. I want to show you a couple of things actually. So this formula right here that I said we seldom need, saves time but is seldom necessary. I pointed out that if you combine these two equations, that's what produces this other equation. And so the thing I guess I'd like to make sure you understand, the thing I thought was really hard about physics is, and I mentioned this before different ways, but was the fact that the physics teacher seems to have command of these like 20 formulas and always just seems to know which one to grab and so forth. But the reality is there's not a bunch of formulas. There's just a couple. You're in a spot because of how far you are in math to understand we created these two equations right here entirely because of calculus. So position, velocity, and acceleration all are related by derivatives and integrals. And then we use these to maybe make another equation like this one. And we've never even, I don't think we've even, well, we used this a little bit with the skier drop in. I think we used it a little bit there. But now, we have all these work and energy equations. And what I'm going to show you is how to take this equation right here and make the work and energy equation. So in reality, we're not going to get different answers than we got before. We're just going to do it in kind of an easier way or a different way. But in a sense, we're going to be addressing questions we've already addressed. We're just going to be doing them using a different approach. And that's why I want to take a minute here and just kind of build these for you. So just for the heck of it, I said, this v squared equals initial velocity squared plus 2 times acceleration times the difference of positions. I want to quickly make that by combining these two, as I said. You tell me, like, what is it going to take to combine these? Notice over here, there seems to be a conspicuous lack of time, like there's no time over there. But see, there is velocities, there is accelerations, there is initial velocities, there is S's for position, like there's everything but time over there actually. So does it make sense to you? That's your hint about how you're gonna put these together. In other words, if I took this top one right here and solved it for t, let's see, v minus v0, initial velocity and then divide by acceleration, that would be time. And then if I took that expression for time and I threw it, I guess, there and there, then I'd have this new expression without time in it anymore. So let's just do it right here. So I guess that means that position S would be equal to 1/2 times acceleration times our new value for t, which is these initial velocities subtracted, and that's squared because t is squared, and then plus initial velocity times time. But again, time is replaced with our new equation for time plus our initial position. Okay, let's see. So what does that produce? What does that leave me if I just kind of start cleaning it up a little bit? Well, let's see if this a squared, I don't know, I'm not sure where to go with this. I think all kinds of things I could do, but let's multiply both sides by 2 because I don't like fractions. So this would be 2s over here. And then this would be a, and if I squared this out, I don't know if this is a good idea or not, but if I squared this out, v minus v0 squared would be v squared minus 2v0 plus v0 squared, and that'd be over a squared. And then plus the rest of this. Doesn't really fit there very good. Whatever, let's squeeze it in there. So, okay, does that do us any good? Well, then I find myself wanting to multiply both sides by a. First of all, this a cancels with one of these a's. And then if I multiply both sides by a, because again, I don't like fractions, it gives me 2as. And then I just have all the rest of the gobbledygook with the a's gone, which is wonderful. So I get v squared minus 2v0 plus v0 squared plus, and I distribute this v0 in, and I get v0 minus v0 squared. And then there's a plus s. And notice I multiplied both sides by a, which canceled this a and this a, but then I'd also have to multiply this initial position by a as well. Again, you don't need to know this, it's just kind of cool. Let's see. Speaking of that, I did something else wrong earlier. When I multiplied both sides by 2, to get rid of this, I would have had to multiply this by 2 and this by 2, not just the ones that I chose. So that actually means that this has a 2 in front of it, and this has a 2 in front of it, and this has a 2 in front of it, if I'm not mistaken. So let's see, what do I get? Well, you might notice it's starting to look a little bit like what we see up here now. So 2as on this side, and I see this is almost the same, so I'm going to subtract it over to the other side as well. And then take a look at what I've got here. I've got a v squared, chang, that's gone. And then I got a minus 2v v0 plus 2v0. And then I've got minus 2 of them plus 1 of them, which is just minus 1 of them. And so perhaps you can see the equation up above then. And so, you don't need to know that, but it's just kind of cool to know you can make these things for yourself. And that's why I said you don't need it. It took us an extra step in different places not to use this equation. But this equation's not new. It's made from those original 2. So that's just kind of neat to see. So of course, if I solve for v squared by leaving it on this side, and I add v0 to the other side, and then I see they both have a 2a in them. So if I take a 2a out, then I have the exact formula that we have there, which is kind of fun. Just algebra. So don't need to know that, but I just think that's kind of a cool confidence builder. You've had a lot of math, and so a few minutes spent time on that, I think, is worth something. Now let's take a look at this work and energy business a little bit. 14.3 work and energy. So these are physics ideas. You wouldn't necessarily remember this, but you can understand that velocity and acceleration and position are things you would want to think about if you're moving, because it's kind of like, well, I'm moving. Okay, cool. Where are you right now? How fast are you going? Are you increasing or decreasing your speeds? Those are the three questions that you would ask. But why would somebody in physics or somebody in engineering want to know about work and energy? Like, what do those even mean? Why? What are those words? What are those words about? Well, I think I'll let the equations answer that for you. My guess is you probably don't have a great answer for that. Like, what does work mean? Well, I think, I went outside and I moved a bunch of bricks, over to the other side of the house, and my wheelbarrow. I was like, oh, that was a lot of work. It was like hard. I sweated. Energy, well, you kind of be like, well, I didn't eat any lunch. And so it really was hard for me to do that work because I didn't have a lot of energy. And so I was really energetic and I got a lot of work done. You might have that's a conceptual understanding of what those words are, but notice they kind of have something in common. Like, if you have no energy, you don't get much work done. If you have a lot of energy, you get a lot of work done. Well, consider this. So we just spent a little time staring at an equation we seldom used. But now we're going to use it. So made from the position equation. And I actually didn't show you that so much to kind of prove that it was true, or even to kind of like teach you a little about algebra or whatever. I just wanted to show you that it's like that came from something. Like, the fact that we took the time to do it, I think, is the important part, not the fact that all the algebra worked out. It's just that came from position and velocity and acceleration. So again, of course, this is just an equation that tells us how velocity and acceleration and position are all related to each other. Well, consider this then. Since often the initial velocity is 0. Now, in the case of, say, and we're going to talk about a problem like this today, let's say a skier is, like right here skiing down this hill. Well, they're going to have an initial velocity there. And so right there, they would have a velocity, but, ultimately they started from up here. In other words, if this was the start, then they didn't have this. At some point, they didn't have any velocity. So that's kind of the idea I'm getting at here. So I'm just saying, to simplify this thinking a little bit, I'm sorry, I forgot the squared. Often that's the case. Even if it wasn't the case, does it make sense? You could subtract v squared or v0 squared. You could subtract this to the other side and you still have a number for velocity there. So it's kind of velocity in general. But if I write out what we have here, and I want you to notice something really cool about this. Do you agree that because this is like where you started and this is where you finished, do you understand that's why you're subtracting those two? Because it's kind of like, oh, I was 8 feet in the air and then I fell to 3 feet. Oh, well, then what distance did you actually travel? Well, you subtract them and you get 5. And so collectively, really, this is just like the distance. That's distance d. So I'm just going to replace that with a distance. I haven't done anything. I'm just simplifying that a little bit. Now let's do something really interesting and really simple. And again, I bet you didn't know this from physics. I'm going to do some basic algebra. I'm just going to multiply both sides by mass. Why am I doing that? Well, I don't know. Let's just look and see. This should start to look a little familiar to you from physics. And if I divided that 2 over, just, and again, you don't need to divide it over, I'm just dividing it over. Does the left side of that look familiar to you now? I don't mean I remember it so much, but do you remember seeing that in physics? And then, thank you, Daniel. And then lastly, what have we been calling this all term right here? What's another name for A times M, given that A is acceleration and M is mass?
Force.
Yeah. One of the most important equations that exists. Mass times acceleration is just force. And so in the end, what we have here is really a force times the distance. And so my point is, this is defined as energy. Again, let's think about that a little bit. Why would that be called energy? Well, I just said a minute ago, it's like, oh yeah, I had to go do some work. I had to move those bricks around the house. Does it make sense? That's a combination of how heavy were the bricks and kind of, how fast did I work? If I was really energetic, does it make sense I'd have a lot of velocity? And so the fact that mass and velocity are kind of connected to energy, it kind of makes sense. Or you might think, oh, I got hit by a train the other day. Well, that's a combination of how big was the train and how fast was it moving. If it's a big train, it has a lot of mass, but it has a really low velocity, that's still a lot of energy. And think about it like a car. Your car is still going to get wrecked if the train's just barely moving. Or you've perhaps heard of, injuries that people have gotten where something isn't moving very much, but they just got in the wrong spot, like the car just kind of bounced against the wall, but their hand was in the way, that kind of a thing. So, energy is a combination of how heavy is it, and also, how fast is it moving? And so on the other side of that, you have a bullet that doesn't weigh very much, but it's moving really fast. And so, if that hits you, that's also a lot of energy that's been put into you. So I guess I just want you to think about that. It's not just velocity, because if you get hit by something really small, that doesn't hurt you at all, because it doesn't have much mass. If you get hit by something really big, but it just barely bumps you, like a car just barely tapped you, it didn't squish you in the wall, it just bumped you a little bit. It's like, I got hit by a car. Well, yeah, it was only moving half a mile an hour, so it didn't hurt me. So the fact that energy is a combination of mass and velocity, I think that should feel good to you conceptually. But notice this side is kind of what physicists has renamed work. But notice the important thing here is they're actually the same thing. Energy and work are actually identical. It's not just that these are two concepts, they're actually the same exact thing. And again, like, what about work? Force times distance. Yeah, I lifted a heavy object. I lifted it 1 inch. Okay, well, that wasn't near as much work. If you lifted a heavy object like a mile, that's a lot of work. I think about this when I ride my mountain bike. I'm at the bottom of the hill. I weigh 180 pounds. My bike weighs 30. So I've got to haul 210 pounds up to the top of the hill. That's a lot of work. Takes a lot of energy, you might say. And so, it's a combination of how much weight. Remember, force is just pounds. And then how far did you move it? You could take a light weight and move it a bunch of times or a long distance, and it would be a lot of work, or a heavy weight and move it a very short distance, and it'd be a lot of work. So again, I think what's cool is, and as I said, I bet you didn't know this from physics, these are just the same formulas that you've already been working with. These didn't just come from nowhere. They didn't just fly out of some physicist's mind. They're not that hard to make. So we just made them for ourselves. That's kind of cool. And so in the end, we just got mass involved. Does it make sense that, back here, there wasn't any mass wasn't involved? But of course, mass or weight is an interesting part of life. If you're going to get something done, how much it weighs is a really important part of it. So it's almost like we just introduced it because it's kind of a part of life. I got to move those bricks. Well, how much do they weigh? That's going to be a lot of work. So introducing M to this was natural for a physicist, or natural for people to just kind of want to understand what it takes to kind of get stuff done in the world. And because this creates a new equation, the idea is just that it deals with quantities that we would be interested in. So you got a motor that's going to hoist something up. We went and looked at that tower crane a few weeks back. It's like, that thing's going to do work. It's going to lift something up. It's going to spin, drop it somewhere else. Well, you got to understand how much work that is in order to stick the right motor in there so the thing doesn't burn up and so forth. So anyway, just a little bit of conceptual underpinning. The other thing I want to say, a couple other things I want to say about this really quickly is just think about units. Like, what would the units of these be? Since they're equal, they're the same exact units. But what would the units be for 1/2 times mass times velocity squared?
Joules or kilogram meter square per second square.
Yeah, you got 1/2, which is just a number, and then you got mass, which we always say is in kilograms, and then you got velocity, which is in meters per second. But we have two of them, right? So we have kilogram meters per second squared. So the unit of energy's unit is a kilogram meter per second squared. You can appreciate that's a pretty unwieldy name, right? And that's kind of a strange unit. And so again, quite understandably, I think somebody says, let's make up a name for that. Well, what's that name gonna be? I could just make up something new, which physicists did, and Daniel rightly told us, a joule. But also think about this a second, think about this a little bit more. Left the G out. Kilogram meter per second squared times meters. Didn't we already have it? If I break it up like this, didn't we already have a name for that? Kilogram meters per second squared, Daniel said this too. That's actually a Newton. So a Newton meter, the unit for this is really a Newton meter, or again, because it's so unwieldy, another name is invented, joule. So energy is actually measured in joules. So that's kind of cool. And let's see, what would this be in standard system then? So mass is actually pounds divided by feet. Is that right? Pounds divided by acceleration, feet per second squared.
You can just go off the work one. So you get force in pounds times distance, so it's foot-pounds. It's a bit easier that way.
Yeah, you're exactly right. And maybe I should just go there first. Let's go ahead and do that. I talked about energy a little bit, but let's talk about, work. What about force times distance? What would be its units? Well, we said force is in newtons and distance is in meters. Oh, look, it's the same thing. So these are producing the same exact unit. That's just kind of interesting to note. And to Daniel's point, in our system, force would be in pounds and distance would be in feet. So it's foot-pounds. That'd be the unit. That'd be our unit, if you will. Which, let's see, has that been renamed? I want to say it hasn't been. I don't think there is a name for that. We'll talk about horsepower tomorrow and a few other things, but joule is a metric unit. It's not in kind of our standard system. So just formally write that. So metric, we would either say Newton meters or joules. Whereas in the standard system, we just say foot-pounds. I'm a little curious, what if we kind of finish this, since mass would be equal to force divided by acceleration. That's why I was saying in our system, I'll erase this, but mass then would be a force in pounds times an acceleration, which would be in feet per second squared. And that'd be multiplied by velocity squared, which would be feet per second also squared. And notice, because down here, the foot is not squared, the only thing left would be feet, pounds, foot-pounds. So that's just kind of cool to notice the units work, I guess. So really the gist of today then is just that you would be able to kind of play around with this equation here. And so notice on my note sheet, that's sort of the very next thing we're looking at. And everything that I just talked about, as far as you don't need to, prove or do anything we just did. In a sense, you don't need to do anything we've just done in any problems. Everything that you need to know is right here. There's work, there's kinetic energy. Notice it's kinetic energy from physics. Why is it? It's energy, but why did I call it kinetic energy here? What's kinetic? Kind of a,
It's the energy that's stored in the motion of an object.
yeah, it's motion. So there's potential energy, which is really work. Potential energy, where you have a force and you lift it up a distance, and now you got a weight that's way up in the air, if you will. There's a lot of potential energy there. So kinetic energy is really the energy of motion, and notice it's got velocity in it. So there's sort of the energy of position. I kind of like to think of this as the energy of position, and this is the energy of motion. But you got those equations, and you got the units for them, and so great. That's all you need to know. So does this second formula then, this is what I want to go use right now for a problem in a second. Does this formula make some sense to you then? This is basically saying the initial energy. Imagine a skier already in motion. So it's like they've got some energy right now, plus whatever work you do to them. Like for instance, gravity is pushing on that skier, and so then they just start going faster and faster. There's a force of gravity and it pulls on them for another 6 feet or whatever. And so now they're going to be going faster. And so this is going to be equal to then the final energy. Do you see the logic in this formula? So let's use that for something. Let's see, what shall we use it for? Maybe this one. Yeah, let's do this one. So you should recognize this as a problem that we've done before. And so you don't need, in one sense, you don't need to know anything. You don't need to know anything I said today to get everything right about this question. But again, the question ultimately, you notice I called it a skater, therefore there'd be negligible friction. But we did this exact problem earlier in 14 point. I want to pull this up really quick just because I want to show it to you. I pulled it in here. Back in chapter 13, this is the question we did in class. So we had a skier ski down the slope, and we figured out how fast the skier was going at B, and that was with the hill pushing on them, and then they flew through the air, and we figured out where they landed at C. And in the case of C, the only thing we figured out was, what distance is that? How far did that end up flying, and how long did it take? But the interesting questions here, there's a number of interesting things a person might want to know. But one of the things that would be nice to know that today happens to be really easy to help us figure out is just like the velocity right there. So if I call this A and this B and this C, like the velocity at C, just interesting things to know, like the velocity at C. How fast are you going when you hit the ground? Because that's going to determine how dead you are as a result of this foolishness, which we didn't even figure out before, but we certainly could have. And so that's why I said determine his velocity at the end of the ramp and upon landing. And if all we're concerned with is the velocity and not distance and so forth, then this is actually, really easy to figure out. Well, let's do that. And notice as I hinted at a second ago, mass is involved here. And so since mass is involved, it makes these problems a lot easier to do in metric. Does that make sense to you? I just showed you a second ago, but if you're in the standard system, mass is kind of ugly because you actually got to take force and divide by acceleration to get it. But let's just see what we get for this problem here using the principles of work and energy. So we certainly know there's the mass of the skater. And by the way, that'd be the skater plus the skateboard. The ramp is 22 meters. It does no friction on it. So we went to a lot of trouble to figure out the velocity at B before. I notice starts from rest, which is sort of code for V0 is 0. And there's no initial velocity. So, okay, what's our equation? Well, we've got our initial energy plus whatever work is done on us will be equal to our final energy. So in our case, this would be really, I'm going to do this in a different color just so I'm not getting rid of it, but really this would be like our velocity at A. That equation right there, which is no different than, that's why I took the time to develop this, no different than any equation we had before. Okay, well, what do we know? We know our velocity at A is 0 since we're sitting there at rest. So that just leaves the force times distance thing. But what do you do with this? What's the force and what's the distance? Is the distance 22 meters? Well, the answer is yes. If the force is going in the same direction, then the distance can be 22 meters. So you'd have to convert your force using 72 degrees to sort of change the force. Well, let's kind of do that. What would that force be? Again, this is kind of a free body diagram thing where where you would say, okay, well, I know my, thanks to gravity, which is straight down, force is mass times acceleration. So it's not just 48. This is the disadvantage, as we've seen. So whatever that is, obviously around 48 times 9.81, we're getting 470.88. And I'll add newtons to that. But we would like to see how much of that is going in this direction. That's kind of our force in that direction. Since that makes a right triangle, and since this is 72 degrees, then that force right there would be 470.88 times the cosine of 72. So I actually get a force of 145.51. So notice that's the force that's in the direction of travel. I'm looking at my arrow, not liking it. I need to draw it nicer looking. So the force is 145.51. And the distance would be 22. So in other words, you had to modify the force of gravity to get that distance. And so then you would say, okay, great. Force 145.51, distance 22. The cool thing about the other side of the formula is notice there's not much over there. There's mass and force at, and the velocity at B. Well, notice I know my mass, it's 48. And so, hey, look, I'm going to be able to find my velocity for B, and that's all I have to do. That's kind of cool. So that number's still in my calculator. I say times 22. I multiply both sides by 2. I divide both sides by 48. I get 133. I take the square root of that and I get 11.55. So that's my velocity at B. How else could this be done though? Do you have to modify your force? So this is kind of one option. Hey, back again. So I want you to notice the kind of another creative way to look at this, because again, my overall goal is to teach you how to think, not just how to get problems done, but how to reason about and to trust yourself that you can think about this a little bit. Could we do this in a slightly different way? Could we use our force of 470.88? The answer is yes, except for what would the distance have to be? Or how would the distance be different? I can't just say 22 again, because I obviously wouldn't get the same answer. Certainly my mass is 48. Anybody have any thoughts on that?
It'd just be the vertical distance.
Yeah, it's just the direction in which that force is happening. In other words, I can use this force of 470.88, but then this would have to be my distance. So would you agree then that you'd have to take, well, 22 and multiply it by the cosine of 70, I'm sorry, the cosine of, yeah, 72 degrees. Do you notice that ends up the same thing we just did a while ago though? Like over here, we took 470 and we modified it by the cosine of 72 to change the force. Well, over here, we're just taking 22 and modifying it with the cosine of 72. It's the same exact math. We're going to end up with the same exact number when we do this. So just rewriting this up here, since that was 470.88 times the cosine of 72. In the end, we added 470.88 times the cosine of 72 times 22. Isn't that exactly the same thing we have down here? So the important thing to take away from this is the force and the distance have to be going the same direction. You got to be pushing that work, pushing that object kind of in the same direction for this to work. And so we're going to get the same exact answer then. So notice neither of those is any easier than the other one. You had to do the same thing in both cases. It just depends on how you want to think about it. But I suppose the really cool thing about this is, what if this person's path, and this is where this gets really cool. What if this path was not so straight, but it was like this? And they ended up here. Can you appreciate that the net change in your distance vertically is no different now? It's like, it doesn't matter how you got there. You were at A, you got at B, who cares how you got there? You know how fast you're going now. That's what's amazing about this. Whereas with the previous method, the fact that that was straight was really important to us. Does that make sense? Because we said, oh yeah, we're going the same direction the whole time. Well, now we're all over the place. And we're just saying, if you pay attention to energy, you just say, well, you had a certain amount of potential energy up at A, and then you gave some of that up to get down to B. And so whatever speed you're originally going is going to be augmented or increased by that amount of work. And now you'll be going a different speed. And all you need to know is the vertical. So part of me wants to say that this one is superior. I notice we need that exact fact because we're about to cruise through the air in the shape of a parabola, right? And that was a whole separate problem for us in a previous section. But now we're saying, who cares what the path is? The first part of this, from A to B, the path was straight. And now the path is on a curve. But do we really care? The answer is no. I could have skipped B and just went straight to C as far as that goes. I could have said, I know based on work and energy, what's happening there. Now, just for the heck of it, let's go back and kind of make a note to ourselves that this was sort of the from A to B part of this problem. Now let's separate that and go from B to C. And then in a second, we'll go just straight from A to C. It won't make any difference. So our same original equation, mass times initial velocity squared plus the work done equal 1/2 times the final velocity squared. Except again, in our case, let's call this the velocity at B and this the velocity at C. And so now this is, in a sense, a little more fun because we're at B, but we know we already have some initial speed now, so that makes us a little more interesting. So now let's just start plugging stuff in, plug and chug. I know my mass is 48. I know my velocity at B is 11.55. I know my force straight down, we said, was 470.88. That's straight down. If that's true, then what's our distance straight down? Well, that's given. I don't even have to modify it, 6. Notice this isn't going to tell me where I land. That's a separate question. If you want to know where you land, then you actually got to bust out the equations we used in the last section. It just depends on what you're after. That's kind of the idea. If all I care about is speed, then I don't have to even know this is a parabola. I can fly that last 6 feet down any way I want to. So I actually know every single thing on the left side. I know the initial energy I have thanks to this first part of the equation. I know how much work gravity did. I know its force and I know how long it's going to act for 6 feet. And then all I have to do is look at the other side and say, well, that's cool. All I have is 48 over there. And so I can solve for velocity at C squared. And so that's really quick. It's really cool. So I multiply all this out. 1/2 times 40 is 24 times 11.55 squared plus 470.88 times 6. Get an answer for that. Multiply 2 away, divide 48 away. And just to record something here, then I get the velocity of C squared is 251.12. So velocity at C when I square root both sides is 15.85. And in this case, because everything was metric, it's meters per second. So that's kind of cool. Irrespective, it didn't make any difference. And for that matter, as I mentioned a second ago, let's just speed this whole process up and go straight from A to C. If you didn't care, in this case, I asked, what's the velocity at the end of the ramp and on landing? So I've answered both of those now. So I sort of had to do that first part. But what if you just wanted to know the landing? Then couldn't you say, as we said before, 1/2 mva squared plus force times distance equals 1/2 mvc squared. I want to go straight from A to C. So since we started from rest and our velocity at A is 0, this whole term goes away. And for force, we said we have a total force of 470, and again, that's vertical. So 470.88. But then my distance, of course, is all these distances put together, which would be 22 times the cosine of 72 to get that first distance plus 6. You okay with that? So 22 times the cosine of 72, that's the top distance, plus 6 in the bottom, whatever that is. And then again, my mass is 48. So I could just go straight to the bottom and see what I get here. So just to double check really quick. I don't know why I'm doing this because it obviously is true. Times 22 cosine of 72. 6, gotta have that in parentheses. Times 2 divided by 48. Yeah, get the same answer. So isn't that kind of cool? So that's one of the advantages of this. It's just another set of formulas that you can draw from, depending on what it is you need. But notice that one of the main things though is notice time is not a part of this. And we'll talk about time shortly, but time is not a part of this. And that might bother you a little bit. It's like you hired somebody to do like move those bricks to the backyard, and one person it took them an hour and the other person took them 4 hours. The point is it took the same amount of work and the same amount of energy. One person just worked sort of slow and lazy, if you will. The other person hustled, but it took the same amount of work to get the job done. But the fact that you might want to distinguish that as a person and say, well, that person did it in 1 hour, good job. And this person took 3. Like, I hope I'm not paying by the hour. If I am, I'm certainly going to hire that first person. They're a better worker and so forth. But, so we'll talk about that in the upcoming section.
But I think that first person gonna charge more, no?
They should, if they can get it done in a third of the time. But the problem is if you see 2 people putting their name out and one says, I'll do it for $30 an hour, and one says, I'll do it for 10, wouldn't you hire the one that's 10? Probably thinking you're going to get a better deal, but not necessarily. And actually, that's what we're going to talk about tomorrow. Like, what if you do want time involved? There's another set of equations, if you will, that categorize that, and that's kind of what power is. So now, again, the part of this that could be confusing is if I gave a final exam in this class and just kind of turned you loose. There's different ways to approach these things. And so, that's a good thing that we're kind of separating this class into midterms and so forth. So in this next midterm, these will be the formulas that you're using, and that'll make it sort of clear which ones to use just to make your life simple. But I hope you're convinced, because of what I started this class with today, that you don't need anything new. You could get all this stuff yourself. I will elaborate on this though by saying, when you did land down here, based on the fact that on our position and velocity equations, does it make sense that you could have figured out your sort of vertical velocity and your horizontal velocity, and then you would have had to use Pythagorean theorem once you found those 2 things? Then you would have used Pythagorean theorem and came up with 15.85 again. So it's nothing new. It just saved us an incredible amount of time. So if our only goal, as I said, was to find the velocity at C, we just did that really quickly using principles of work and energy. So cool. Any thoughts, comments on that?
It does feel kind of funny that we can know the speed, but it really could be coming in any direction potentially.
Yeah,
Given the
isn't
right
that
setup.
weird? I think what Landon said is a very good point. I'm glad you said that, Landon, because I would have said it myself, but I thought of it. But notice it doesn't say anything about what direction you're going. It just says that's your velocity down there, but it doesn't say what direction you're going. That's kind of weird that it doesn't tell us that. That'd be the advantage of having a vertical and a horizontal. And notice if you're a skateboarder, you would care because your vertical velocity is what's going to hurt you. Does that make sense? Like how hard you hit the ground, that's going to be a problem, and what angle you land at and so forth. So, if you wanted to know those things, then you actually need all the equations we did last time. And so these all kind of work together. It just depends on what it is you need to know. And to that end, let's take a look at a fairly challenging question. And this will probably take us the rest of the time. So this is an example of a question that's in your book. This is straight from the book, whereas the last one's one I made up. So you got this 150-pound skier. So this is not in metric. So they're skiing down on a surprisingly a cosine wave. That seems kind of strange, right? Unless this is the X Games and somebody was making this accordingly. This would just be some random mound of dirt. So notice when the skier was at point A, he already had a speed of 5 feet per second. So he had an initial speed. So this is kind of like our velocity. I'm just trying to make sense of the problem here. That's our velocity at A. I'm going to make a note that that's a force, and hence mass would be equal to 150 divided by 32.2. Isn't that acceleration for non-metric or standard problems? And so if I need the mass for something, I'm just noting that to myself because I'll probably screw that up. So it says determine his speed when he reaches B on this smooth slope. Well, again, this illustrates what I was saying before, which is notice he's actually traveling in a totally weird orientation here. But we don't really care like what shape that is. What we care about from what we just did a second ago is really just what's that distance right there? Does it make sense? As long as I just say, hey, his force is vertical, because in this case it's curving. So, you know, in that first problem, the fact that it was a straight slope, I was able to convert the force to kind of the force along that line. Well, this person is changing directions constantly. And so you can't really do it any other way. So I know his force is 150 pounds. And if I could know that distance right there from A to B vertically, then that's all I need to know. Again, what is this word code for right here? If you see that in your problems,
No friction.
no friction. It's kind of a weird thing to say, no friction. So let's just answer that question right there. Well, what is that distance? Well, here's where this is the only place I need the equation. If that mountain was just a regular ski hill and was all undulating and weird, does it make sense you could get the same thing with like a Google Earth? Like you could get an elevation at A, put a pin at elevation A, and then you go to Google Earth and put a pin at elevation B, and you could actually figure out what the distance is, and who cares what the equation is. In this case, it's kind of contrived. We're going to use an equation to get that distance because, you know, this is not, to me, that's the difference between a book problem and an actual project. Would be like, let's come to my house, my driveway just rolls randomly down the hill, let's like shoot a grade, let's get a transit out and shoot the level, the height between those two. I don't need an equation, I just need that height. So let's see, well, in my case, I'm gonna have to figure out the Y value at A. So notice they gave me an X, Y axis. So that's kind of code for, since my equation's got X's in it, it's really a code for 0, like X is 0, I'm right there. So if I stick 0 into that crazy equation, I get 50 times the cosine of 0. You may remember without a calculator that on the unit circle, you're right there. Cosine is the X coordinate. So the X coordinate at that point is 1. So I'm actually 50 feet in the air. At the top of the hill, 50 feet in the air. Okay, well then where am I at B? Notice at B, I'm given a horizontal distance of 35. And so 50 times the cosine of 35 pi over 100. That seems like a weird location. So I find myself thinking, I'm just going to use my calculator. Notice it says pi. That's kind of problematic. That's very problematic. Because it says pi, what do I need to be thinking about on my calculator to not screw this up?
Is it in radians?
Nice job. It's in radians, which is particularly annoying in this class because we're seldom in radians. And so that kind of stinks. And then also they probably should have told us that, right? But we didn't need to be told that. We're smart. So if I type 50 times the cosine of 35 pi divided by 100, this does not come out nice. It comes out 22.699. So I'm just going to call it 22.7 feet. Which means if I subtract those, then D would be 50 minus 22.7, which is 27.3 feet. So there's D. That's all I need to know then. So again, work and energy, 1/2 times the initial velocity squared plus the work that is done will equal 1/2 times the mass for the final velocity, wherever final means. In this case, final is B. And so again, I might decide that I'm going to go back and call this A, and I'm going to call this B instead, because that's what I mean by initial and final. And so, oh yeah, I guess I do need my mass, unfortunately. Mass is 150 divided by 32.2. I did need that. My initial velocity, I was told, was 5 feet per second. Notice the units are all okay. It's like pounds and feet and seconds. There's no weird units. And then I have my gravitational pull, my force. Well, that I don't have to multiply. 150 is a force, and I have to multiply it by acceleration. And I just figured out my distance vertically. Notice it's just so strange that the velocity is, here and here and here. And so these are like pointing totally different directions. The velocity over here is sort of pointing all different directions, whereas this work is just straight down. So it's just kind of not obvious, I think. And so I know my mass. So I know everything I need to know then to get my velocity at B, just based on that alone, no different than before. So 0.5 times 150 divided by 32.2 times 5 squared plus 150 times 27.3. On the left side, I'm going to write part of this out. I got 4,153.23. On the right side, I got 2.33 times velocity of B squared. Better though, just to leave those numbers in your calculator. So if I divide those two, take the square root of it, I end up with velocity at B. Does this seem like a reasonable number? Hence, the velocity at B is approximately 42.23 feet per second. Again, I'm being lazy and leaving units off just because we run out of room, but you're more than welcome to leave all the units in everything you do here, and then you don't have to know what the units of your answer are. They'll come out that way automatically. So that's very closely connected to what we just did. It's just that a minute ago, we were able to use geometry and sine and cosine to get that vertical distance because of right triangles, whereas here, I don't have access to that. So I've got to use the equation they gave me. Very contrived. So cool. Well, I haven't even read the rest of the question. For this distance, the slope follows the cosine curve shown. Also, whew, tough problem. What is the normal force? What is the normal force on his skis at B and his rate of increase of speed? And again, I like that they said neglect friction and air resistance. Those are a thing. There is going to be friction, there is going to be air resistance. But they said ignore them, not that they don't exist. That should worry you. What's normal force?
The force of the ground pushing back up.
Yeah. That's the force of the ground pushing back up on us. Kind of that normal, in other words, that's kind of right there. It's the ground pushing on us. And remember I hope you took to heart that Desmos I showed you the other day, but remember that's kind of related to the normal acceleration. It's like how hard is the ground pushing on the skier right there. Remember that depends on where you are, because it's a combination of just how much do you weigh, but it's also depends on where you are. Like if you're down here and there's a big curve in it, remember the ground's going to be pushing really hard on you right there. That normal force will be massive if you're down there on kind of a curve. And so it isn't just your weight. So that's a little bit terrifying. Rate of increase in speed. What is that code for? That is increase in speed. That's tangential acceleration, not normal acceleration, which is related to the normal force, but actually tangential. So then I'm thinking, oh, wow. So that's asking me about formulas that I've used before pertaining to curvature. Or where did all those go? Right there. It's actually asking me about this stuff. Or perhaps this, right? So there's tangential acceleration. So I'm gonna need that formula. Some of the force is tangent and mass, and that'll give me the acceleration tangent. I'm gonna need that one. And then this one had the sum of the normal forces in it, and that was related to mass and normal acceleration. Again, from that Desmos I showed you, I hope you're getting that. And so if I need to know anything about normal acceleration, then, here's a bunch of stuff up here. So it's like, I'm gonna have to use some of that stuff we did before, since they asked me a little bit harder of a question. So, what should I do? What are your thoughts?
Find the radius.
Yeah. The thing I guess I'd like you to, if you want to get this stuff, you shouldn't think, uh-oh, what are the steps? Just figure stuff out. Like draw a free body diagram and figure out how much of your force is going in each direction. And I don't know what to do. Just start doing what you know how to do. Maybe I'll go get, like Ewald said, I can get the radius. I mean, maybe I'll need that, maybe I won't, but it's like, I don't know, start somewhere. And sometimes these problems can look daunting, but you just think, well, I don't know, let's just go figure stuff out. So let's take Ewald's suggestion and get the radius of curvature where we are. Remember that had something to do with how straight the location was. Notice we're kind of on a pretty straight area, and I would say that looking, if they drew it accurately, that the circle's like here, it's actually kind of facing down. And so, as I said, I don't know if we're going to need it, but let's just go get it. Maybe we will, maybe we won't. So in order to do that, I needed some derivatives. And so let's see, what would y prime be? What's the derivative of cosine? This is a blast from the past in your brain.
Negative sign?
You're right. The derivative of sine is cosine. The derivative of cosine is negative sine. So And that 50 out in front comes along for the ride. So there's a 50 and then a negative sign, and whatever the junk is, it doesn't change. The derivative cosine of junk is sine of junk. So it's pi over 100x. That hasn't changed. Perhaps you remember that we're not quite done though. What else do you still have to do according to the chain rule?
Multiply by the derivative of the junk.
Multiply by the derivative of the junk. And since it's junk times x, then so there's my derivative. So I don't know if this is worth the trouble, but maybe it is. I guess I could put all the constants together. 50 over 100 simplifies, so maybe it is worth it. 50 over 100 is a half, so I end up with negative pi over 2 sine of pi over 100 x. And so my location is at B, which has an x value. Since this recipe, if you will, calls for x, then I could stick 35 into that whole mess. I'm just going to type that whole thing in. Negative pi divided by 2 times the sine of 35 pi over 100. When I type all of that in, I get negative 1.3995. Pretty darn close to 1.4. What is that saying? That's saying, well, that's saying that's the slope. That's the slope. Yeah, that slope would be negative 1.4, negative 3/2. That's a steep slope. Okay, yeah, that's right. That makes sense to me. And it also called for the second derivative, the rho or radius of curvature formula called for that second derivative too. So if I continue, the derivative of sine of junk is cosine of junk. And the constant pi over 2 comes along for the ride. The junk stays unchanged, but again, I've got to multiply by that junk yet again. So another pi over 100. So what does that equal to? If I will simplify it out, I guess that's negative pi squared over 200 cosine of pi over 100x. Notice I still need, if I'm going to know the second derivative, I got to figure out what it is at the point that I'm at. So I got to throw 35 into that. Negative pi squared divided by 200 times the cosine of 35 pi divided by 100. Machine says that is negative 0.022. So do I know everything I need? Yeah, I do. I do know everything I need for rho now, because if I remember right, I'll double check this, but it was 1 plus the derivative squared, all raised to the 1.5 power, if I remember right, divided by, and I know there's something wrong with this. I think that bottom was an absolute value, if I remember right. So it's not negative, in other words. Let's double check this. Yeah, second derivative, absolute value. Everything I said is true. So really that's supposed to be an absolute value of that. So, okay. So 1 plus, instead of typing negative 1.4 squared, I'm just going to type 1.4 squared and raise that whole thing to the 3/2 power, or raise it to the 1.5 power, and then divided by 0.022. And there was a 4 after that. I think I'm going to keep the 4 in there. It's such a small number, I'm worried it's not going to make it accurate. So I got 227.35 feet. Again, I don't even know if I'm going to need this, but it's just kind of cool to figure out. Does that mean something to you in this picture? Again, it doesn't do any good to say, yeah, I understood that stuff from last term then, but now I don't. So I'm glad this question's in here. That's the radius of your circle. That's a big number. 200 feet radius. Yeah, that's a big radius because it's almost straight right there. So, you know, we're talking about a circle that's like, you know, huge radius circle. So that kind of makes sense. Now, I would have thought it made sense if it was 300 or 150 as well. I can't get this, you know, any better than that just from estimation, but okay, so cool. So I know that. I'll make a note of that in case.
Unknown caller.
In case I need it later on, maybe I won't. What else can I figure out that I know?
Normal acceleration now.
Yeah, now that I know that radius and I know my velocity, right? We figured that out a minute ago, so I could find normal acceleration. That's kind of cool. Again, I don't know if I need to know it. That would equal velocity squared over rho, which is, we said 42.23. Don't forget to square it. Close enough, divided by 227.35. Bam, I got 7.844. I think I'll just call it 8.4. So let's see, what would that unit be? Well, logically, it would be feet per second per second. So there's another number I might need, I might not. That's kind of cool. Let's see, what else could I figure out? Well, I figured out everything that pertained to curvature. So now I'm kind of looking at these. And as I said before, we're going to need these two equations now because I was asked specifically about this and about this. So it makes me think I need to get those involved. But when you see forces normal and forces tangent, that should concern you. Because what direction are those? Well, unfortunately, if the skier is here, then those are forces tangent and forces normal. I kind of going that way. In other words, it's not XY axis anymore. We're using the normal and tangential axis to figure these things out, not X and Y. That way it matches the slope that we're on. And so if I'm going to know what forces are, because I have a gravitational weight and so forth, since unfortunately my force due to gravity is going in this direction and that doesn't help me, I've got to convert those. And so this means I'm going to need kind of a free body diagram to figure all of this out. And unfortunately, I don't know what angle I'm at. I don't know what angle the hill's at. Does that make sense?
Well, we've got the derivative though.
Yes, nice job. I do know, I mean, I'd like to know that angle right there so that I can figure out what direction orient my axis. And we said that's very closely related to the slope. In other words, the tangent of the theta there equals the slope of the equation. And we know the slope. So now the work we did, it's kind of cool. It's like not going to waste. That slope right there, the slope of my hill was negative 1.4. So since I have that derivative, I can say the tangent of theta is equal to negative 1.4, and I can actually know what that angle is. So cool. Second tangent of negative 1.4. And you might notice you're going to get radians. And now I find myself wanting to be in degrees. And so I'm going to go back and switch to degrees. And I got negative 54. This is enough to be perfect. So let's just round it off. I got negative 54.46. I'm going to call it negative 54.5 degrees. So, and that looks right. Again, that looks right because wouldn't it be going in the negative direction? Be going down, my slope was down. So of course it would be negative. If I got something positive, that would mean I was traveling uphill, not down. So let's judge their diagram now just to make sense of this. Actually, I'd say they drew that pretty well. They're saying that's 54. That looks a little more than 45. So I'm thinking their diagram's pretty good. Thank you, Mr. Hibbler. So now that I know this, now I'm able to kind of convert everything that I know. So let's see, my force of gravity. What was my weight? Good deal. That's just 150. I don't have to multiply it by anything. It's 150. And more than one way to do this, but let's see, how do I want to do this? I think I'm gonna change, let's see, what would that be from 90? 35.5. That would mean this angle here is 35.5. Since this angle is also 90. I think that's right. So that's 35.5. And so notice so in a sense, I've got force tangent and my force normal is kind of going into the hill, if you will. So let's see, 150 times the cosine of 35.5 and 150 times the sine of 35.5. So for cosine, I got 122.1. For sine, I get 87.1. So now I kind of feel like I can maybe draw a free body diagram in case I need it, and it sort of seems like I'm going to. So I've got this force going kind of down the hill at, that would be the 122. And then I've got this force that's actually going into the hill, and that's the 87.1. So gravity has now been converted to the normal and tangential coordinate system. Are there any other forces on this? Is that the end of my free body diagram? Am I done? The answer would be yes if you're falling through the air, but we're not falling through the air. So what's missing?
The normal force.
Yeah, the normal force of the snow. So the snow is pushing back on me. If I was in the air, then I would just be going down, falling straight down. And so now my free body diagram is complete. So this is at 90 degrees. I don't know if I need to know that. That's at 90 degrees. So I think my free body diagram is complete. Free body diagram just is forces. And so these are all the forces that are acting on me. Gravity pulling me down, snow pushing back on me. And so now I'm free. Now I think I'm free now to kind of try out. I think I'm going to move these over a little bit. Give myself some room and try to finish. I got to get done here so you guys can get out of here. So So I don't know which one to write first, but we got the sum of the forces tangent is equal to mass times acceleration tangent. And I've got the sum of the forces that are normal equal to mass times the acceleration normal. So I'm just going to plug in what I know. I don't know. I don't know what this is all figuring out. I'm just going to plug in what I know. So sum of the forces tangent. Well, that's 121. 122.1. That's the only force that's in the tangent direction. That's it. And that's equal to mass, which unfortunately is 150 divided by 32.2 times acceleration tangent. Oh, cool. Now I'm going to be able to find acceleration tangent. I mean, think about that. 122.1 times 32.2 divided by 150. Bam, I got 26.2. So I was actually asked that question, and you should appreciate that's a good question to ask, isn't it? Because we figured out earlier that at that point in the snow, we were going 42 feet per second. And what we just figured out is, whoa, 1 second later, you're going to be going 26 feet per second faster than that. That kind of makes sense because you're on a pretty steep hill, right? So remember, that's a speed change, not a direction change. So I'm really being pushed on. Well, what about this second equation? Force is normal. Well, I've got the force normal pushing. And by the way, which one of these is positive and which one of these is negative? Or does it matter? I want to say this is positive and this is negative. Do you agree with that? Or does it not matter?
It shouldn't matter as long as you're consistent.
Yeah, I think you're right about that. The reason I wanted to say that is because based on our picture right here, didn't it look like this was round this way, which means, you know, the center of the circle is the direction of positive normal. So that's why I was saying I think I want that to be, but Daniel's right, it doesn't make any difference. So I have two forces. I have 87.1 going positive. I have force normal, which is the snow pushing against me. I have my mass, which is 150 over 32.2. And then acceleration normal. But again, isn't that cool? We figured out acceleration normal. We did need that. So we needed everything we did, which is kind of just nice, coincidental, 7.84. So no problem. So if I take 87.1 minus 150 divided by 32.2 times 7.84, I get 50.57. Call it 50.6. So force normal equals 50.6. What would that force be? That'd be pounds, I guess. That's how hard the snow is pushing on me. Again, it isn't just 87. That's the thing that's interesting here. Why is it not just 87? That's because you're not traveling flat right now. You're not traveling in a straight line. You're being turned, if you will, by the hill. The hill's turning you. It's making you change directions. So we get a slightly different answer than 87 as a result of that. So lastly, I just think it's kind of, these just look like random physics questions, but I think these are all very interesting questions. I'm going to ski down this hill, you know, to this spot. And at that point, I'd like to know how fast I'm going. I'd like to know how fast am I increasing my speed and how hard the snow is pushing on you. Notice the snow is pushing on you. If that had been negative, that meant you're flying, right? That's something else important from the other day. Armed with that, we've really tackled here the 13.4 assignment. So I started this out saying we're in 13.4. You should be able to do the 13.4 questions now. And then next time we'll tackle the 13.5 stuff. and get into power and so forth. Anything you want to ask me about?
Wait, you said 13.5?
13.4, you should be able to do right now.
Oh,
We
14.4.
got
Okay.
through 13.4, but Thursday we'll do some.
Isn't that the
example
wrong
things.
week or wrong chapter? I mean,
Say again?
aren't we on chapter 14 now?
Yeah.
Did I say
It's
that wrong?
14.3. Yeah.
Yeah, 14. I'm sorry, I looked at the wrong thing. Yeah, I'm sorry, I looked at the wrong thing. 14.3. I was looking at the previous section. Yeah, you should be able to do the 14.3 stuff. Did I write that wrong in my initial note too? No, I didn't. So yeah, should be able to do 14.3 some. I'm actually not sure about 14.4 because we got 14.4 and 14.6, but off the top of my head, I can't remember where the transition is. But I'm pretty sure 14.3. Anyway. I hope you're a hair smarter now than we were when we started.
All right. Thank you, Doug.
Thank you. See you guys.
Yeah. See ya.
Yeah.
See ya.